This series of videos is to give an outline and basic introduction to the book Contributions to the Founding of the Theory of Transfinite Numbers by Georg Cantor. The book that I'm going to be referring to is the Dover edition, and the book is made up of two parts. The first part is quite a lengthy introduction by Philip Jourdain, which goes on for a good 80 pages or so, and gives sometimes quite detailed background information on Georg Cantor and the state of play of mathematics during the 19th century. The second half of the book is Jourdain's translation from the original German of two of Georg Cantor's published papers. The first is from 1895, and it's called Contributions to the Founding of the Theory of Transfinite Numbers, first article, and the second work from 1897 with the same name, except funnily enough it's referred to as the second article. Cantor's two works give a fairly in-depth introduction to his theory of transfinite numbers. Starting in the first article with the idea of power or cardinal number of an aggregate. An aggregate here is used instead of the more modern word set, and I'm going to stick to the more or less original terminology, or at least the terminology used in the translation. But in the same article he introduces ordinal types of simply ordered aggregates before moving on in the second article to well-ordered aggregates, ordinal numbers and some properties of ordinal numbers, and in particular transfinite ordinal numbers belonging to what Cantor calls the second number class. The aim of this series of videos is simply to present Cantor's work in more or less its original form. So I don't aim to try to correct any parts of Cantor by throwing out what Cantor wrote and replacing it with updated or corrected material. Having said that, I will from time to time make comments on various aspects of what Cantor wrote. For example, if there's something that has, over the years since Cantor published this work, received some kind of further clarification, then I might comment on this. And I might draw more attention from time to time to certain points that I feel are important, and I might from time to time elaborate or try to clarify things that I feel are a little bit difficult to follow from Cantor's work itself. But these are not meant to be rewrites of Cantor's work, but simply to help and aid in the understanding of his work. Ultimately though, whatever Cantor writes is what we'll accept, whether it's deemed correct or not from a modern perspective. I'm going to be using the terminology used in the book, which might occasionally differ from modern usage, and some terms might not be in modern usage at all. During the video, the focus really is going to be on the concepts. I'm not going to be giving a blow-for-blow account for Cantor's work, in the sense that I'm not going to be going through the proof of every single theorem. I will mention theorems, and I will go through some theorems that I think are interesting, but this series of videos is really not meant to be a fully comprehensive analysis of Cantor, just an overview. So I just want to give a brief overview, really, a bit of a sketch illustration really about how these transfinite numbers came about. So in the introduction to the book, in Philip Jourdain's introduction, he gives quite a not fully detailed, comprehensive background and history of the development of these numbers, but he gives a bit of an idea about where they've come from. Because one problem that I think a lot of people have with these infinite or transfinite numbers is that they seem quite contrived and a bit forced, a bit of a forced idea that we've got different types of infinity. After all, when we get to infinity, surely just adding 1 to infinity doesn't make it any bigger, because it's already as big as it can be. But I think herein lies the mistake, and it's kind of an incorrect image that people have in their mind of what these things are. So the transfinite numbers in which that Cantor introduced are not really anything to do specifically with size. They're to do with the ordinal type of an aggregate, for example. And the ordinal type of an aggregate only has a certain dependency on the size of the aggregate. So we might think normally as, for example, 10 as representing something that an aggregate or a collection of 10 objects. And as the number of objects gets greater and greater, then we can see that this number seems to represent something that's bigger and bigger and bigger. So something with 100 objects is going to be bigger than something with 10 objects, and the number 1,000 seems to represent something that's bigger than 100, which represents something with 100 objects. But the transfinite ordinal numbers that Cantor introduces have nothing really to do with this, at least only in a limited sense. They're to do with the ordering that's placed on the objects of an aggregate, and these numbers allow us to distinguish the ordinal types, the types of order that we see in these aggregates. But I'm going to give a bit of a brief overview about where these transfinite numbers come from, and it turns out they come about in quite a natural way. So if we consider, for example, a finite interval, it might be closed, it might be open, it doesn't really make any difference, A, B, on the real number line. Then if we consider now a system of numbers, an aggregate of numbers taken from this finite interval, moreover an infinite aggregate of numbers taken from this interval, and we call it P, then a well-known principle from analysis is that an infinite set of, or an infinite aggregate of real numbers in a finite interval must have at least one accumulation point. There might be many accumulation points, but there's going to be at least one. And we can call a point in this system, in this aggregate, a limit point if given any kind of open interval, no matter how small, about that point. So let's say this is the point that we choose, and we just take a really small interval around it, that no matter how small we make that interval, there's always still going to be an infinite number of points in this aggregate in that interval, no matter how small we make it. And that's what we mean by a limit point. Well, what we can find is the aggregate of limit points of the aggregate P. So we'll call it P primed. But P primed itself is just an aggregate of real numbers, again, from the finite interval AB. So it itself may have limit points. If it's finite, then it won't have any limit points. If it's infinite, then it will. So we can continue this process. We can go on to find the second derived aggregate. So these are called derived aggregates. The derived aggregate of P, the derived aggregate of the derived aggregate of P, etc. So if this is finite, then the process terminates. A finite aggregate of real numbers in a finite interval is not going to have any limit points, so the process effectively terminates. Whereas if this is infinite, it's still an aggregate of real numbers from AB, so we can continue the process. We can find P prime prime primed. And we can continue this for as long as we want. So let's say we get to P new, then this may be finite, a finite aggregate, it may be infinite. If it's finite, again, the process terminates. And in that case, we'd say that P is of the first kind, but of the nth species, if it did actually terminate here. So if it terminated here, then it would be of the first kind of the third species. But this might be an infinite aggregate as well, in which case we continue. And it might be that by continually doing this, finding these derived aggregates one after the other, this process never terminates. Well, in that case, we can take the limit aggregate. We can find the limit aggregate. So this would be really the aggregate of limit points that persist through all of these and never kind of fall away. So at each stage here, there's potentially points that are going to be falling away, that maybe were limit points here, but are not limit points here. But there might be some that persist through all of these, in which case we get an aggregate, and we'll call it P infinity. So again, P infinity might be finite, in which case the process terminates. or it might be infinite, but it's still an aggregate. It's still an aggregate of points from the finite interval AB, so there's no reason why we can't just continue this process and get p infinity plus 1 and p infinity plus 2, and we just continue until the case arises that we get a finite aggregate for one of these derived aggregates. It might actually be the case that we never get to a finite aggregate, in which case this process is just going to keep going on and on and on. Again, we could take the limit of this and we'd get p to infinity, and then the next one would be p to infinity plus 1, etc. So the question is, when would this process terminate for such a p? And would it even terminate? Could we just keep going through and finding more and more derived aggregates in this way, taking limits and then continuing the process, taking another limit, continue the process? Or would it actually stop at some point? Would it be forced to stop? So this was something that Cantor thought about, spent a lot of time thinking about. It's not something that I'm interested in here. It's not the focus of the work that I'm going to be going through. What we're interested in doing now is actually abstracting this idea of generating these numbers. So we're going to move away from the derived set, the derived aggregates, and we're just going to look really effectively at the numbers, these superscript numbers. So what we get is a sequence of numbers 1, 2, 3, 4, and we can continue this process as simply just adding 1 to generate more and more numbers in the usual way. So this is no surprise whatsoever. So this is what's called Cantor's first principle of generation. Given any number, we can get the next number along by just adding 1 to it. But we can't postulate that there is a greatest number here without a logical contradiction coming about. But what we can do is we can use what's called Cantor's second principle of generation, which is, for a sequence with no greatest, posit the existence of a new infinite number. And this doesn't lead to logical contradiction. So we can posit the existence of an infinite number, infinity. But in fact, we're not going to use the symbol infinity. We're going to use the symbol omega. And I'll be explaining briefly later in this video why the symbol omega was chosen instead of the usual infinity symbol. So then we can go back to the first generation principle. Add 1, add another one. But again, this is a sequence that doesn't have a greatest in it. So we've got to posit a new infinity, a new infinite number, 2 omega. But then we go back to the first generational principle, 2 omega plus 2, and then we get to 3 omega. And then we'll get to potentially omega times omega, or omega squared. Let's write it as omega squared. And then I'll get omega cubed at some point, omega cubed, and then potentially I'll get omega to the power of omega, and omega to the power of omega to the power of omega, etc. So this, we get this unusually large series of numbers, extremely large series of numbers, that's not even exhausted by numbers of this form. We would eventually get to potentially another number that breaks out of this omega symbol. We get something like, I don't know, some alpha. But then we start again, alpha plus 1, alpha plus 2, alpha plus 3, etc. And we can just keep using these generational principles to produce more and more of these transfinite numbers. Philosophical considerations can't be ignored when considering Cantor's work, as the creation or discovery, depending on your point of view, and introduction of these transfinite numbers was closely bound up with Cantor's philosophy. The introduction of these new numbers was considered a revelation by some, but by others were flatly rejected and considered a travesty, such as Kronecker, who referred to Cantor as a corrupter of youth. Cantor had a very firm belief in the concepts of actual completed infinite aggregates and even completed infinite aggregates of a seemingly arbitrary size. The decision by Cantor to use omega instead of the usual infinity symbol to denote the first infinite transfinite integer was due to the fact that the infinity symbol was used for what Cantor considered the improper infinite, which is something that increases in size to exceed all limits or decreases in size to be exceeded by all limits. Omega was used to indicate that Cantor considered his new numbers to be proper or actual infinities. The notion of an actual infinity is quite common nowadays amongst mathematicians, who will, without a second's thought, speak of the set of integers, the power set of the real numbers. In other words, these things exist in a fully completed form. And this was a highly controversial concept at the time of Cantor for some mathematicians. Completed infinities were borderline theological. Cantor's view was that he was simply making discoveries, though, that these things existed and he was just discovering their properties. His belief was that all that he was discovering was being given to him by God, and that he was guiding Cantor in his discoveries. But oddly enough, despite his belief in the existence of transfinite numbers and the actual infinite, he never accepted the existence of infinitesimals, which seems a bit contradictory. These considerations regarding the existence of actual infinities and the status of the infinite within mathematics was a key driver in the development of much of the mathematics that came about during the first half of the 20th century, and indeed Cantor's theory led to the introduction of what we now know as the axiom of choice, which was a highly controversial axiom. We'll see briefly in this series of videos that Cantor was making use of this axiom unconsciously in his work. Of course, now the axiom of choice is used by mathematicians without any hesitation, but this certainly wasn't the case in the first half of the 20th century. Interestingly, Cantor considered there to be two kinds of reality. Regarding the first type of reality, for example, he says, and I quote, "We may regard the whole numbers as actual insofar as they, on the ground of definitions, take a perfectly determined place in our understanding, are clearly distinguished from all other constituents of our thought, stand in definite relations to them, and thus modify in a definite way the substance of our mind." So the first kind of reality is concerned with the kinds of objects in our minds. And as long as these objects are clearly distinguished from one another and don't lead to any contradiction, then they have this first kind of reality. Of his second kind of reality, he says, again, I quote, "We may ascribe actuality to them insofar as they must be held to be an expression or an image of processes and relations in the outer world as distinguished from the intellect." So Cantor's second kind of reality concerned external objects. He also believed that the first kind of reality implies the second kind, but that the pure mathematician is only concerned with reality of the first kind. His transfinite numbers evidently are of the first kind of reality, and therefore are legitimate objects of study for the pure mathematician. In fact, Cantor considered all numbers, transfinite, rational, irrational, and complex, as just as existent as the positive integers. So this is where I'm going to finish this short introductory video. In the rest of the videos in this series, I'm going to be going through both articles of Cantor's work. The next video is going to start with aggregates and their cardinal numbers, which I invite you now to watch.